In this video, we will explore amplitude modulation. Amplitude modulation is an analog communications technique. It allows us to transmit a signal over long distances and also to transmit multiple signals at once. Then, we perform demodulation to analyze the transmitted signal, perhaps to listen to it if the signal is audio. I will illustrate exactly what is happening during the process of amplitude modulation and demodulation in both the time domain and in the frequency domain. I will start off by illustrating the overall process. Suppose that in the time domain, we start off with an arbitrary signal x of t, and it can be anything. Let's say something like this. What we're going to do for amplitude modulation is we are going to perform a few steps. We're going to take our signal x of t, and the first thing we're going to do is we are going to multiply it by a cosine with a frequency of omega sub c, and I will explain this shortly. From this, we get an output signal y of t, which is x of t multiplied by cosine of omega c t. And this is a signal that we're actually going to transmit, and that's going to go through what we call the channel. The channel can be either the wireless airwaves or through a wire or any other medium, and there will be some kind of a noise introduced at this point, but we're not going to focus on that in this tutorial. At the receiving side, after it goes to the channel, we are again going to multiply by the same exact cosine as we used right here. And this will give us some signal, we'll call it w of t, and then that is going to go through a low-pass filter, and the output is going to be what we will term x sub r of t, or our received signal, and this should in theory be the same exact thing as x of t. So this is the full amplitude modulation process. So why does this help us to communicate effectively over the wireless channel? It has to do with the frequency content of x of t. If we use the Fourier transform, we can find the frequency content, we'll call it x of omega, of x of t. And the way that this may look, and this is going to be just made up for illustrative purposes, is that x of omega is going to be a triangle in frequency, and I'm not going to go into the details of the Fourier transform, but we have to have symmetry about the y-axis, which is why it might look something like this. And this is just a typical kind of representation of an arbitrary frequency content. It's not actually related to the x of t that I had drawn up here, but again, it's simply to illustrate what I'm going to show. Now, this signal itself would not propagate very well because it's at very low frequencies. So instead, what this procedure is going to do that I just presented up here is it's going to shift the frequency content of x of t to higher frequencies, which are good at propagating through the airwaves. So the multiplication by this cosine of omega sub c t, what that's going to do is it's going to shift everything up and down in frequency by that frequency, by the frequency of the cosine, which is omega sub c. So if we then draw our signal y of omega, that is the Fourier transform of y of t, we're going to get the exact same signal as x of t, the same triangle, except now it's going to be centered, instead of around 0, it's going to be centered around omega sub c and negative omega sub c. Again, the symmetry has to be preserved here. So what this effectively did, this multiplication by the cosine, is it shifted the entire frequency content up and down by that frequency of the cosine. Then it goes to the channel, and once again here, and we're going to assume there is no noise, it gets multiplied by the same exact cosine. That means that once again it's going to get shifted by the same exact amount up and down in frequency. So if we then draw the frequency of w of omega, so that's after getting multiplied by the cosine again, we're going to find that we have our triangles all the way out at 2 omega sub c, and negative 2 omega sub c for the symmetry, and also back around the origin. And this is because, once again, we just shift everything up and down in frequency by that carrier frequency, by the frequency of the cosine that we multiplied by. And so we get this kind of a spectrum. And now the last step in the process is a low-pass filter. That means that we are going to take just this component, and that is going to be the signal that we're actually going to recover. So now the spectrum of x sub r of t, so x sub r of omega here, is just going to be what we get after low-pass filtering, which is just this. And this is, in theory, exactly the same as our original x of omega, if no noise was introduced in the channel. And that's the whole idea. The point is that we can't readily transmit this signal up here, but we can easily transmit y of omega. We can transmit this signal, or its corresponding y of t. And then, to demodulate, that is to bring things back down and to get back our signal that we're actually interested in, we have to perform this demodulation technique, which is, again, just multiplying by the same exact carrier, or the same exact cosine, and low-pass filtering. This is what things look like in the frequency domain. Now, I will illustrate what things look like in the time domain, because it's important to be able to see both sides of what's happening. In the time domain, suppose that we have our signal x of t that looks something like this. Just some kind of arbitrary waveform. After multiplication by that cosine that we saw, we're going to get y of t, which looks like this. Now this is that cosine that we multiplied by with a frequency of omega sub c, which is a high frequency. And since we multiplied our original signal by it, it takes on the shape, the overall shape of our original signal. In fact, if we superimpose our original signal on here, we can see that this perfectly follows the shape. This is why this technique is called amplitude modulation. It's because our signal modulates the amplitude of that cosine, which is called the carrier. So we have this carrier at a high frequency, just a high frequency cosine, and it takes on the shape, the overall envelope shape here, of our original message signal. And now this blue signal here, this quickly oscillating signal, is good at being transmitted through the airwaves, which is whereas the red signal is not. That's why we have to perform this. So this is what happens in the time domain. This blue signal corresponds to what we had seen right here. That is that y of t. This is its spectrum, supposedly, just a made-up spectrum. But this is what we actually have in the time domain. That's what we transmit. Now, the next step, of course, is to get w of t, and that's going to be to multiply this blue signal once again by that same carrier, by that same cosine. And what we get if we do that is something like this. This is what it would look like. And once again, if we superimpose our original signal here, our x of t, we see that it still follows this shape. And now this is w, and you can see you have components at twice the frequency of the original carrier, and also the overall shape back down around 0 frequency. So now if we low-pass filter this whole thing, we're going to get back just the red signal, and we're back at our original message. So that's what happens in both the time and in the frequency domains when you perform amplitude modulation. One more thing that's worth mentioning here is what's called frequency division multiplexing. And the idea here is to be able to transmit multiple signals simultaneously and still be able to recover each one individually. So to illustrate this, suppose that we have 3 distinct signals, and I'm going to draw these each one in the frequency domain right away, so they have some kind of corresponding time domain representation, of course, but I'll just draw them in the frequency because that's where we're really going to illustrate how this works. And let's just call them x1, x2, and x3 of omega. The way they're going to look, just to give them distinct symmetrical shapes, the first one will be a triangle, the second one will be a semicircle, and the last one will be a rectangle. Now the idea is to transmit all three of these but be able to recover one of them individually selectively. This is exactly what happens with radio stations, where all the radio stations are being transmitted simultaneously, but then you choose which one you actually want to listen to. And the whole principle here, the whole idea is that now our y of t, or our y of omega as we're going to draw it in frequency, is going to consist of all of these together, but at various carrier frequencies. That is, the first one we're going to place at omega c1. We're going to multiply it in our original scheme that we had shown here by some frequency omega c1. And the second one we're going to multiply by omega c2, some other frequency. And the third one we're going to multiply by omega c3. And of course you have to keep in mind that we have to have these components on the negative side of the spectrum as well for symmetry at negative omega c1, negative omega c2, and negative omega c3. So we transmit this, and we can pack as many signals in here as we really want, and then all of these are being transmitted simultaneously. Now if I drew this in the time domain, it would be just a bunch of overlapping sinusoids in the shape of these individual messages, and it would look like nonsense. But in the frequency domain, all of them are non-overlapping in theory, and therefore what we can do is we can say, okay, I want to listen to just station 2, x2, and so I will apply a bandpass filter around this signal, and then we are back at exactly where we were right here with y of omega in this illustration, because now I've gotten rid of every other signal. After this bandpass filtering operation, what I'm left with in the frequency domain here is going to be just this signal at omega c2. And then I can perform my exact same demodulation once more by multiplying by the carrier at frequency omega c2, and that'll shift things back down. I then again apply my low pass filter to just pick the thing around 0 frequency and get rid of the components at twice the carrier frequency, and I get the station that I was interested in. And that's the idea with frequency division multiplexing. So altogether, we have seen how to perform amplitude modulation, demodulation, and multiplexing in both the time and the frequency domains.